Previously, we used ray tracing to locate images that were formed by lenses. And now I'd like to get a little more algebraic about it. So what you have seen drawn here is a case 1 situation. The object distance s is more than 2 times the focal length, although absolutely nothing would change in this argument if it were case 2 and with some sign conventions, which we'll get into for a moment, cases 3 or 4. So this will actually work out in general. Now I've only drawn 2 of the 3 useful rays. I've drawn the paraxial ray, which goes in parallel to the optical axis and out through the far focal point. And I've drawn the central ray, which goes through undeflected. And I've used those two to locate the image here. Now I've said that the object height is h and the image height is h prime. Now the idea here is that we can play some games with similar triangles. Specifically, we can look at this pair of triangles right here that I'm outlining in sort of a bright green. This triangle and that triangle. So it includes my object. Here includes my object, the central ray, the optical axis, the central ray, the optical axis, the image. Now these two, this angle right here and this angle right here, are the same by alternate interior angles. There's a right angle here and here by construction, which means that this angle here and this angle here are also the same. So in other words, these two green triangles have identical angles, which makes them similar triangles. So what this means is we can set up a proportion and write that h prime is to h as, I'm going to leave some space here. You normally say s prime is to s, but remember here that since the image here is inverted, we want to recognize that it's upside down versus the object. So we'll put in a minus sign to recognize that. And we will call this the lateral magnification. So that's one of 2 things that we can pick out of this from similar triangles. The other one, which I'll mark in sort of a light purple here, is this triangle right here and this triangle right here in light purple. So now we're using the bit of the focal ray after refraction. That's one of the shared legs of our triangles. The optical axis is another one. Here we have the image here, and we have the principal plane here, but the amount of the principal plane here is the height of the object. So it turns out that you can again set up that h prime is to h as minus, then it's this distance right here is to that distance right there. Now you're going to have to use a whole bunch of tedious algebra, and I will spare you the tedious algebra and get to the punchline. When you set up the similar triangles here and turn the crank on the algebra, you'll get that 1 over s plus 1 over s prime equals 1 over f. Now this gets alternately known as the thin lens equation. Oops. And when we redo this for mirrors, once we figure out how to relate the focal length to the radius of the mirror, this will also be the mirror equation. We haven't done mirrors yet, but we'll get the exact same, we'll get these two exact same results when we do this all again with mirrors. So this is why I'd just like to call this, and this isn't any official name, but this is why I like to call this the most useful equation in optics. Now, I only demonstrated this for a case 1 situation. You should be able to convince yourself pretty much immediately that literally nothing would change with what I did here if this was case 2. And I will just have you more or less take on faith that this also works out for cases 3 and 4, with the proviso that we do some special things with our plus and minus signs. So this is the sign convention that we will be using. This isn't the only possible one. This one is the one known as the left light convention. It's probably the most widely used of the sign conventions. Yeah, I can spell. But it's not the only one out there, so you may find yourself as you go through other books occasionally, for reasons that make sense for whatever the author is trying to do, they'll use something else. But this is far and away the most common one, and it's the one that we'll be using in these videos. So I'm also going to put in the quantities for mirrors just for completeness sake. That only adds one thing to the mix. So plus, minus, I'll have 3 columns here. So the focal length, and in the case of a mirror, the radius of curvature of the mirror, in the left light convention are positive if the lens or mirror is converging, and negative if it is diverging. In all cases, the lateral magnification, the object height, and the image height are positive if the thing is upright, and negative if it's inverted. And then as far as object and image distances go, they are positive if it is a real object or a real image, and negative if it is a virtual object or a virtual image. Now, in this treatment, we will only ever look at real objects. Virtual objects are a thing that can happen in multi-lens systems. It's beyond the scope of this treatment. That adds a case 5, 6, 7, and 8 for the ray diagrams. I'll just say they're a real pain to deal with, and I have actually encountered working physicists settle their bar tabs by betting each other on their ability to actually draw ray diagrams with virtual objects. So it's a thing. You might run into it in some advanced optics treatment somewhere down the road, just so you're aware. But as far as we're concerned, objects will only ever be real in this treatment. But as far as images go, remember, a real image is one you can form on a screen. A virtual image is one that you have to look through the lens or the mirror to see it. So with these choices of plus and minus signs, you can go back and do this same kind of argument for cases 3 and 4, and also similarly for mirrors when we get to it. You could do a similar whole argument again. And you will get, in each case, out will pop out the lateral magnification relationship and the most useful equation in optics. So let's go ahead and try making this concrete here by taking a look at a problem. Let's say I have a converging lens with a focal length of plus 40 centimeters. So I'm drawing my optical axis and my principal plane. Since it's converging, I'm just drawing a little cartoon of a converging lens. Maybe try to do a little better than that. That was worse. Okay, third time is as close as it gets to a charm. I'll go ahead and locate in my focal points. So it's converging. So both of my focal lengths here are plus 40 centimeters by the left light convention. And I am going to stick a 5 centimeter high object at 30 centimeters in front of the principal plane. So my object distance S here is going to be plus 30 centimeters. Remember, in this treatment, objects will always be real, so we'll always have a positive number. But in more advanced treatments, weirder things can happen. I'll let that be for those instructors to discuss. Anyway, before you ever tackle, and what I want to find here is I want to find the image distance and the image height. So again, I will just mark in here that this is plus 5 centimeters, the plus because it's upright. So we're trying to find the image distance and the image height. Okay. Always, 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 when you're dealing with these things, you should always start by drawing a ray diagram. And even before you do that, you should always ask yourself, is this case 1, 2, 3, or 4? So pause the video and ask yourself that. Yeah, it's case 3. It's a converging lens, and the object distance is shorter than the focal length. So that means that we know that the image that we get will be virtual, upright, and magnified, because that's what all case 3 situations are. So let's go ahead and draw the ray diagram, because remember, a carefully drawn ray diagram will always give you the correct answer. So if need be, if you're stumped doing this algebraically, just get out the rulers and protractors and very carefully draw your ray diagram. You'll be good to go. So there's your paraxial ray. Let's go ahead and draw in the focal ray. Again, here I use dotted lines for work lines. I use dashed lines for when I'm backtracking. Okay, something about like that. I'm going to go out parallel. And then finally, our truest, bestest friend is the central ray that always just goes through undeflected. Like I say, in general, we like to use 3 rays just because it helps us to catch any mistakes we might make. All right, so now we'll take each of these rays. Oops, let's do a better job than that. We'll take each of these rays and we'll go ahead and backtrack them to locate the image. Something about like that. I'm not saying I'm doing a great job. Okay, it's something about like that. So there's my image, and I can see from the construction that it is indeed virtual because the rays are diverging here. They'll never form on a screen. I have to look this way through the lens to see, in this case, a bigger version of the thing I'm looking at. So this is staring through a magnifying glass. So this is the image distance that I want to know. And from the diagram, I can immediately tell that the answer better be negative. Similarly, this is the image height that I want to know. And looking at the ray diagram, I can immediately tell that it's going to be positive. Okay. So with all these problems, usually the way you go is you just start setting up the most useful equation in optics, solve for the image distance, and then once you get that, you can use the magnification relation to get the image height. So let's do that. So 1 over s plus 1 over s prime equals 1 over f. Now we got to be really careful with all the reciprocals here, so let's take the algebra a little more carefully than I might usually do. So I'm just subtracting 1 over s from both sides. Now I want to get s in the numerator, but before I can do that, I need to get this onto a common denominator, which is what I'm about to do now. So to get this on a common denominator, I would multiply top and bottom here by s, top and bottom here by f. So I'll have 1 over s prime equals s minus f over sf. Okay, now I can cross multiply my way around to get that s prime is equal to sf over s minus f. Now, this is super mega important. When you substitute in your values, you absolutely must keep track of your plus and minus signs. Because remember, the plus and minus signs tell you important things like converging or diverging lens, real or virtual image, things like that. So you need to be very careful about that and make sure to keep track of your plus and minus signs. So I like, even when it's positive, I like explicitly writing in the plus sign just so I know I didn't drop a sign. So the object distance was plus 30 centimeters. The focal length, because it's a converging lens, was plus 40 centimeters. Then here again, the object distance is plus 30 centimeters. And I will be subtracting a plus 40 centimeters. So if I punch this through into my calculator, this is going to give me negative 120 centimeters. Now do not drop that minus sign. You really need to keep that minus sign. That minus sign is telling us that this is a virtual image. You have to keep this minus sign when you plug into the magnification relationship, because if you don't, you're going to mess up whether it's upright or inverted. So speaking of that, let's go ahead and find what our image height is. So we remember that the lateral magnification, which by definition is h prime over h, is also minus, don't drop that minus sign either, s prime over s. So rearranging, I can rewrite this as h prime equals minus s prime over s times h. So h prime is going to be, I have this algebraic minus sign here. Got to keep that straight. Then the s prime is minus 120 centimeters. I got to have that one too, or things aren't going to work out right. Over plus 30 centimeters times plus 5 centimeters. Now you see both of these minus signs cancel, and this gives me a plus 20 centimeters. And this tells me that the image is upright. If I had dropped this sign or that sign, I would have accidentally thought that it was inverted, and then I'd be staring at my ray diagram and be very confused. So, moral of the story here is you cannot play fast and loose with your plus and minus signs. You really do need to keep them. Alrighty, so in the next video, we'll go ahead and pick up more on this with mirrors. See you in that video.